We are starting a little mini unit on sequences and series. So first I want to define what a sequence is. So a sequence is a function A whose domain is the set of natural numbers. The terms of the sequence are written as a sub 1, comma, a sub 2, comma, a sub 3, comma, dot, 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 because the pattern continues until we get to a sub n. The number a sub 1, and this is just a subscript, is called the first term. A sub 2 is called the second term. And in general, a sub n is called the nth term. Now you guys have done sequences of numbers from when you were probably quite young in math, where you'll be given a pattern of, or you'd be given a set of numbers and you're looking for the pattern. That is just describing a sequence. So we're just going to go a little deeper now. So for this first example, we're going to find terms of sequences, and the instructions say to write the first 5 terms for each sequence. So I'm going to, this is the rule right here. They're telling me a sub n equals 5n minus 2. Now, notice this looks a lot like y equals 5x minus 2. So you're going to see some similarities to some things that we already know. So I'm going to start by finding a sub 1. And this is basically saying where n is 1. So I'm going to have 5 times 1 minus 2. So I get 3. And that's the first term in this sequence. A sub 2, I'm going to plug a 2 in. So I get 5 times 2 minus 2. So we get 8. And then I'm going to do the same for a sub 3. And we get 13. And a sub 4. And we get 18. And finally, a sub 5. And we get 23. So then the sequence of numbers, a lot of times you'll see sequences written out like this: 3, 8, 13, 18, 23. Because sometimes we'll go the other way. I might give you a sequence of numbers and ask you to find the rule. Right now, we're being given the rule and finding the sequence. So on part B, looks a little more complicated, but we start off the same way. So to find a sub 1, remember you're letting the n equal 1. So I have negative 1 to the 1 plus 1 power times 1 squared. So negative 1 to the second power, negative 1 squared, is a positive 1 times 1 is just 1. So the first term in my sequence is 1. Then I have to find a sub 2. So I have a negative 1 to the 2 plus 1 power times, this time n is 2 squared. So negative 1 to the third power is a negative 1. 2 squared is 4. So I get negative 4. A sub 3, we have negative 1 to the 3 plus 1 power times 3 squared. So this time negative 1 raised to an even power is going to give me 1 times 9 is 9. Then a to the fourth power, we have negative 1 to the 4 plus 1 power times 4 squared. So this is raising to an odd power, so it's going to be negative 16. And then a to the a sub 5, the fifth term, negative 1, 5 plus 1 is 6, times 5 squared. That's going to be a positive 25. So my sequence of numbers, I have a 1, negative 4, 9, negative 16, and 25. Now notice in this, and it would keep going. Notice how these are perfect squares. but the signs are alternating. So this -1 raised to the power is what's causing the signs to be alternating. So on part C, again, we're doing the same thing. So to find a sub 1, n is equal to 1. So I have 3 times 1 plus 2. And here we'll have 1 squared plus 3. So I get 5 in the numerator and 4. So we have 5/4. A sub 2, I'm going to have 3 times 2 plus 2. 2 squared plus 3. So I get 8/7. And a sub 3, and in the denominator we'll have 3 squared plus 3. So we get 11/12. Now, a lot of times you can see a pattern even without, continuing on the process. Okay, so you can see I paused it and went ahead and did the last two. So you might want to pause this and copy down that information. So again, this is not hard. If I were listing out my sequence, now obviously this pattern is a little different, but you would just list out these sequences of numbers. All right, so if the terms of an infinite sequence, and what's meant by infinite sequence, my ... this pattern continues on indefinitely, so it's an infinite sequence. If the terms of an infinite sequence get closer and closer to some real number, the sequence is said to be convergent. And to converge to that real number, and I'll show you an example of that. A sequence that does not converge to any number is divergent. Some sequences are defined by what's called a recursive formula. One in which each term after the first term or first few terms is defined as an expression involving the previous term or terms. So with a recursive formula, you have to know what you had before to see what you get next. So here's going to be an example of using a recursion formula. So here they tell you that the first term in the sequence is 2, and they tell you this formula for how to get the next term. You're going to take, to get the next term, so think of the a sub n as the next term. You're going to take 3 times, and think of this a sub n minus 1 as the previous term. I'm going to write that down. So think of this as the next term. You're going to take 3 times the previous term. Minus 1. We'll subtract 1. Now, they tell you where to start too, because they say n is greater than 1, which means I'm going to start with 2. By the way, the value of n, and as I said in the very first statement, n is the set of natural numbers. So we don't have, n can't be a half or anything like that. They are natural or counting numbers. So I'm going to start with let n equal 2. So then I want to find a sub 2. So to find the second term, I take 3 times the previous term, which would be a sub 1, and then I subtract 1. So remember, we're told right up here that the a sub 1 was 2. So then I get 5. So then to find the next one, we have to find the first 4. We already know the first 2 now. So to find the next one, I let n equal 3. To find that term, I'm going to do 3 times a sub 2. So I get 3 times, my previous term was 5. So we get 14. And then for the last one I need to find, to get the fourth term, I take 3 times the previous term, which is a sub 3, and subtract 1. So I get 3 times 14, and then when I subtract 1, I get 41. Okay, so for this next one, we're told a sub 1 equals 5, and we're trying to find the first 4 terms. We already know the first one. So to get a sub 2, I'm going to take, so remember, I'm letting n equal 2. So that means I'm going to take a sub 1 plus 2 times, and then n is 2, so I have to plug a 2 in here. So then that gives me 5, because that's what a sub 1 was, plus 4, which is 9. So that's my second term. So now I let n equals 3. So to find a sub 3, which is the third term, I take the previous term, which was a sub 2, because they tell me n minus 1, and n is 3, plus 2 times n. Well, remember now n is 3. So then I get the second term was 9, plus 2 times 3 is 6. So my third term is 15. To find my fourth term, I let n equal 4. So a sub 4 is going to be the previous term, which was a sub 3, plus 2 times n, which is 4. So I get 15 plus 8, which is 23. All right, so that's how we use a recursion formula. Not hard. It helps to write down the value of n, and just be careful. So series and summation notation. So we have this notation that we use. Summation just means you're going to add. You're going to add something up. So the sum of the terms of a sequence is called a series. Is written using summation notation. The symbol, and this is the symbol sigma, looks like that. The Greek capital letter sigma is used to indicate a sum. So a series, a finite series, that finite just means it ends, is an expression of the form, and here we use an S to stand for the series, or you can kind of think of it as the sum. And you're going to be, if you were adding up in terms, then you'd be doing a sub 1. So it's basically taking the first term plus the second term plus the third term. And so you're just adding up all the terms. So the notation we use with this sigma notation is, and this just means add them all up. So we're taking a sub 1. We'd start with a 1, a sub 1, and then we'd plug in a 2, and then plug in a 3, all the way up till we get to n. An infinite series is an expression of this form, S sub, and you'll notice that's an infinity symbol because it never ends. It keeps going. And we'll see some specific examples later on where we'll have an infinite series. So for this first one, how do you use summation notation? If you take what this tells you right here, this value right here is your starting, and it's called an index value. So we're going to start with a 1, and then this number at the top is your ending value. So this tells me to start with a 1. So if I want to evaluate this, I'm going to take 1 squared plus 1 plus 1. And then I'm going to add to that the next term. I go to the next number, which is a 2, because I'm going to go 1 up to 5. So we take 2 squared plus 2 plus 1, because I'm just letting j equal 2. Then I'm going to let j equal 3. So I get 3 squared plus 3 plus 1. Then 4 squared plus 4 plus 1. And then 5 squared plus 5 plus 1. And then I stop because that's where it told me to stop. So when I add these up, I'm going to get 3 plus, this next partial sum is 7 plus 13 plus 21 plus, and the last one's 31. And then if I add these all up, I get 75. So that would be my answer. So here's a Cool little feature on your calculator. You might want to get this out and try it. If you hit alpha and then the window key, notice number 2. You see this word summation and it has the little symbol shown there for you. Now you don't have to use a J. If you want, you can use, we can use an X, and I'm going to go from 1 to 5, and I'm going to type in x squared plus x plus 1. So really that value is, I mean, it was just a variable. So, and there we have the answer, 75. So you can appreciate what your calculator's doing for you, because basically it's taking a 1 and you know, working out that partial sum, taking a 2, taking a 3, and then calculating that. So kind of a nice feature to do. However, the calculator won't help you on this one because we're asked to write the terms for each series and evaluate the sum if possible. But notice here, I don't have actually the value. I'm just being told to plug in, you know, so that all I can do is say plug in a 1. So I get b sub 1. Then I'm going to plug in a 2. And remember, I'm adding them all up. So I get b sub 2. And then I plug in a 3, b sub 3, and then a 4, and then a 5. But I can't get the answer. I can't evaluate it because I wasn't actually given an expression or anything that I can evaluate. So that's actually the answer. And on the next one, I am going to start with a 1. So now they give me starting values. So they tell me x sub 1, x sub 2. So I'm going to be able to plug some values in. But I still can't really use my calculator on that. So if I start this, I'm going to plug a 1 in. So I'm going to ignore these and plug them in later. So I'm going to have 2 x sub 1 minus 5. That's my first term in the series. And then I'm going to have 2 x sub 2 minus 5. And then I'm going to plug in a 3. So 2 x sub 3 minus 5. And then a 4, 2x sub 4 minus 5. And then I stop because the index value tells me to stop there. But now I can plug in those values. So I get 2 times 3 minus 5. I'm just going to actually work those out. So here we get 6 minus 5 is 1. Plus, here I'm going to plug in the 5 right here. 2 times 5 is 10. So I get 10 minus 5, which is 5. Here I'm going to have 2 times 7, which is 14, minus 5, which is 9. And then last, 2 times 9, which is 18, minus 5, which is 13. And if you add these all up, you get 28. So not hard. So we have some special summation properties and rules. The properties are on the bottom of your page, but then you have to flip it over to see the rules. So again, dealing with if we have a sequence, if we have 2 different sequences, and you can see the terms listed out there, and we're told C is a constant, then for every positive integer in, the following hold. If you have, and you can come back, I'm not gonna really like address every single one of these. On part B, if you have a constant times a sequence, you can pull the constant out in front of those, in front of that summation, in front of the series. If you are, remember the summation means you're going to add them all up. If you have the summation of 2 different series that have been added together, you can split them apart. Whether it's being adding or subtraction, you can split those apart. Then we have some other special summation rules down here that kind of lead to some special sequences that you might want to just take note of, because we might have some examples where you want to come back and just get a shortcut. So you might be given a series in this format and you want to be able to come up with a rule for it. So these are some that would be a place to come back to look at. So I'm going to do some examples using these. So for this first one, the rule that I would be using on this, if you look at the very first one, summation properties part A, it said that if you have the summation where I goes from 1 to n of a constant, it's just n times the constant. So here's n, here's a constant, so then my answer is just 50 times 12, so I get 600. All right. Basically, there's nothing to plug in. So you're really just doing a 12 plus a 12 plus a 12 plus a 12 all the way up to 50. So you get 50 times 12. On part B, this 3 is a constant. This, well, it's kind of a coefficient, but we've got this. And so using the properties, property B says that I can pull the 3 out. And I'm still doing this. So now if you take a look at what that would be, now take a look at this one right here now, because that's what I have. So this tells me what formula that I can use to evaluate this. So then the formula that I would use, this is going to be 3 times n, which is 35, times n plus 1, which is 35 plus 1, over 2. And if you do the math, I don't have this memorized or anything, I have it worked out, is 1,890. Now, if you didn't want to use those special formulas, you could use your calculator to evaluate this with the way that I showed you on that. And I'm fine with that. As a matter of fact, let's do the last 2. I'm going to pause this. So you should pause the video and do these with your calculator just to practice. Okay, so you should have gotten 1,205 for part C. Here you can see what I punched into my calculator. And part D is 215. And that is actually the end of the first section. So you will have an assignment that you should be able to complete from these notes.